In computer vision, I would say that whenever it is possible to use active illumination methods, that is, when you can control the lighting of the scene, you should. Because when you can, it turns out that you can recover information about the scene, such as shape, reflectance properties, with much greater reliability and accuracy than is possible if you just use the general ambient lighting of the scene itself. So active illumination is very widely used in computer vision. I would say it's a multi-billion-dollar industry unto itself. It's used in various domains, such as medical imaging for surgery and other applications, or factory automation. In the context of factory automation, if you think about your smartphone, say, for instance, you simply wouldn't have a device of that sophistication if active illumination methods were not being used to aid robots assemble these parts together, but also for visual inspection of these parts after they're manufactured. That's all being done using active illumination methods. And you may be surprised to know that even when you talk about something like the driverless car, it turns out that it uses active illumination to figure out the three-dimensional structure of its surrounding. You don't see this, you don't see the illumination being used because it tends to be done outside of the visible light spectrum. But it is being done, and it's absolutely essential to the performance of these systems. So in this lecture, what we're going to do is talk about a variety of active illumination techniques, and in particular, our goal will be to focus on ones that seek to extract the three-dimensional shape and reflectance properties of objects in the scene. So we're going to start off with an active illumination method that we've already discussed, which is photometric stereo. If you think about it, in the case of photometric stereo, you're actually using the illumination of the scene from different directions, source directions. You capture a set of images, and from this set of images, you're able to compute the surface normal at each point on the surface of an object. And then later, you might integrate these normals to get the three-dimensional shape of the object. So that really is a form of active illumination or controlled illumination. We'll once again very quickly review photometric stereo and then look at ways in which we can extend photometric stereo to make it even more powerful. Next, we're going to look at structured light range finding. By the way, range finding is synonymous with depth finding. And so the idea here is to throw out light patterns onto the scene, a small number of light patterns, using, for instance, a digital projector, capturing images using a camera, and then being able to compute at each point the depth of the point in the scene. So we're going to start off with a class of techniques that use a small number of brightness levels, discrete brightness levels, or discrete colors in order to construct the light patterns. So once we do that, we're going to then look at how we might use continuous brightness patterns, that is, light patterns that have continuous functions of brightness, and throw these out, and it turns out that you can construct such a pattern and then simply change the phase of the pattern, shift the phase, in order to capture multiple images and reconstruct the three-dimensional structure of the scene. This technique is called phase shifting. And next, we're going to look at some structured light systems, impressive ones that have been developed in different domains. We'll see how they are actually functioning today and helping us in the context of factory automation, performance capture, and also digital archiving of, say, for instance, cultural heritage monuments. And finally, we're going to talk about time-of-flight methods. So in the case of time-of-flight, what we're trying to do is measure the amount of time it takes for light to travel from a light source, strike a surface, and then arrive at a sensor. If you're able to measure that time very accurately, then since you know the speed of light, you can figure out exactly how far the point is in the scene. So these are techniques, time-of-flight methods, are now becoming very popular, have begun to surface in devices such as smartphones, and in the next decade, they're going to become ubiquitous.